Welcome to this. This is our fifth half-hour lecture on fundamentals of transport processes. In the first lecture, I had given you an introduction to why we study transport processes and what is it that we will be studying in this class. We had started our study of transport processes with dimensional analysis in the last two lectures. I had explained to you the distinction between fundamental and derived dimensions in the last two lectures. The fundamental dimensions are mass, length, time, temperature, current and light intensity. And in this course we will primarily be dealing with mass, length, time and temperature. And I had shown you how all the derived quantities can be derived from these fundamental dimensions. And all of the quantities of interest to us in this course, the fluxes, mass, heat and the shear stress, the temperature difference, the concentration difference, the velocity difference and those coefficients that are in there, the diffusion coefficient for mass transfer, viscosity for momentum transfer, thermal conductivity and specific heat for heat transfer. We had solved a problem in the last lecture, a simple case of the flow of the settling of a particle in a fluid. This is acted upon by a gravitational force, maybe a buoyancy force, and therefore the net force will be proportional to the difference in density between the particle and the fluid. That is a body force. It acts at every volume element within the particle. In addition, there is the drag force, a surface force, due to the stress exerted by the fluid on the surface of the particle. And that surface force acts to retard the motion of the particle. It arises because when the particle moves through the fluid, the particle generates fluid flow around it. And that fluid flow inevitably results in fluid friction and therefore a dissipation of energy. And this manifests itself as a drag force. This is a surface force. This is basically the stress exerted by the fluid on every surface element of the particle, summed up over the entire surface. That gives you the total drag force. And as we had seen in the last lecture, this drag force could be a function of the particle's size, diameter, the velocity of the particle, because if the particle doesn't move, there is no drag force. Okay, so it's basically a relative velocity between the fluid and the particle, the density and the viscosity. And based upon dimensional analysis, we had obtained dimensionless groups. In this case, there were only three dimensionless groups. One of them is the dependent dimensionless group. The drag force is the dependent quantity. It depends upon the velocity, the density, viscosity and so on. So, a dimensionless group, which is a non-dimensionalized drag force, is a dependent quantity and it depends on these independent quantities, that is the ratio of the diameter of the particle to the size of the container, and this dimensionless number, the Reynolds number, which I had introduced in the last lecture. Reynolds number is the ratio of inertial forces to viscous forces. The inertial forces are basically due to the fluid inertia and they contain the density and the velocity in them. The viscous forces are due to the fluid friction. The ratio of these is the Reynolds number. We had gone and interpreted this relation a little bit beyond dimensional analysis. What I had told you was that in this kind of a relationship, if the Reynolds number is small, that is particle inertia is much smaller than fluid inertia, then the drag force should not depend upon the particle inertia. If the fluid inertia is much smaller than the fluid viscosity, then the drag force should not depend upon fluid inertia. It should depend upon the viscosity alone. In that case, the regime is when the Reynolds number is much smaller than 1, when the fluid inertia is much smaller than the fluid viscosity. In that case, the density of the fluid should no longer be a relevant parameter, and therefore we had still further simplified this. Okay. The scaled drag force has to be just a constant. Okay. That constant, of course, we do not know from dimensional analysis. You need to do an exact calculation, and you will find that that constant is equal to 3 pi in this case. It's called the Stokes drag law. Okay. When fluid inertia is much larger than fluid viscosity, the situation is a little more complicated. Okay. You might simplistically think that fluid viscosity can be neglected altogether. However, in that case, there is effectively no friction at the surface, and therefore there will be no drag force. Okay. Fluid inertia is the equivalent of convection of momentum. Fluid viscosity is the equivalent of diffusion of momentum. And as I told you in the last lecture, even though convection can transport momentum within the fluid, ultimately at surfaces there is no convection perpendicular to the surface, and therefore ultimately the momentum has to be transported due to diffusion alone. So when the convection is much faster than the diffusion, it is not always possible to neglect diffusion. That is a point that we will come to a little later. Okay. It's not always possible to neglect diffusion. You may need to consider diffusion within thin regions close to the surface. Okay. So that is the summary of the dimensional analysis that we had done in the previous lecture. Now let us turn our attention to the subject of the present lecture, which is a correlation based on dimensional analysis for the heat transfer in a heat exchange. Okay. Rather than talk about the total transport rate, the total transport of heat per unit time across the surface, it is conventional to talk about the average flux. This is basically the heat transported per unit time across the wall divided by the area of the wall. Okay, so, it is called an average flux, and that average flux is of course dependent upon the average temperature difference, okay, between the inside and the outside. Okay. In addition to the average temperature dependence, it also depends upon other dimensional quantities. Okay. Of course, it will depend upon the diameter of the tube, okay, with dimension L, the total length of the tube, okay, with dimensional L. Okay. It depends upon the thermal properties of the fluid, okay, because the thermal properties do affect the rate of transfer of energy across the surface. Thermal properties in this case are the specific heat, and the thermal conductivity. And of course, the rate of heat transfer will also depend upon at which the fluid is bringing in heat into the tube due to convection, okay, because it is the heat that is convected along the flow that is being transported across the surface, and that rate at which heat is being brought in due to convection will depend upon the flow velocity. And this will also depend upon the mechanical properties of the fluid, okay, the density and the viscosity. Okay. So, we now have a total of 9 quantities here. The dependent quantity is the average flux, and that depends upon all of these other quantities: the temperature difference, the diameter, length, specific heat, the thermal conductivity, the velocity, density, and viscosity. Okay. And of course, so now the program is clear. We have to write down the dimensions of each of these, and then based on dimensional analysis, see how many non-dimensional groups are there, and then try to derive expressions for these non-dimensional groups. So, the heat flux, okay, we had derived equations, the dimensions of each of these, okay, in the previous lecture, if you recall. Okay. So, the heat flux has dimensions of m t power minus 3. Okay. The delta T, the temperature difference, has dimensions of temperature itself. Okay. The diameter has dimensions of length. The length of the pipe has dimensions of length. Okay. The specific heat, okay, if you recall, okay, we had derived that. Okay. The specific heat has dimensions of length T power minus 2 theta inverse. The thermal conductivity had dimensions of m, L, T power minus 3 theta inverse. Okay. The average velocity had dimensions of length per unit time. The density was a mass per unit length. Okay. And the viscosity, if you recall, okay, we had got it over here, m L inverse T inverse. Okay. So, there are now 9 quantities, okay, and there are how many dimensions? 4 dimensions, because you have mass, length, time and temperature. Okay. So, total of 9 quantities, 4 dimensions. So, you should have 5 dimensionless groups, okay, which determine this average heat flux. One is the dependent dimensionless groups and the others are all independent dimensionless groups. Okay. However, we can do something more than just dimensional analysis, okay, if we recognize that there are 2 different kinds of energy that we are talking about here. Okay. One of them is the thermal energy, okay, due to the temperature that is being transferred across the surface, and the other is the mechanical energy due to the kinetic energy of the fluid itself. Okay. Now, in the event that there is no interconversion between thermal energy and mechanical energy, we can consider thermal energy to be a different dimension, okay, because it is not interconverted to mechanical energy. So, as far as the transport is concerned, the thermal energy is in itself conserved quantity. Okay. If we make this distinction between thermal energy and mechanical energy, we get one more dimensional in this problem, okay, and that is the thermal energy. Okay. And all the thermal quantities can be expressed in terms of thermal energy, while all the mechanical quantities can be expressed in terms of the mechanical energy. Okay. So, let us write down another dimension for thermal energy. Okay. As H. Okay. Then the thermal quantities, the heat flux, the specific heat and the thermal conductivity have now got to be expressed in terms of this thermal energy H. Okay. So, this we are going one step beyond dimensional analysis and identifying another independent dimension. So, what is the heat flux in terms of the thermal energy? The heat flux is equal to energy transferred per unit area and unit time. Okay. So, therefore, this will have dimensions of H L power minus 2 T inverse. Okay. How do we get the dimension of the specific heat? Okay, the thermal energy is equal to m Cp delta T. Therefore, the dimension of specific heat, okay, has to be the dimension of thermal energy times mass times theta. Okay. Therefore, the specific heat will have dimensions of H m inverse theta inverse. Okay. And finally, the thermal conductivity. Okay. It has to be obtained from some relation which involves a thermal conductivity in which we know all other quantities. Okay. In this case, it is the constitutive relation, the Fourier's law for heat conduction. Okay. Q is equal to minus K delta T by L. Okay. Now, Q has dimensions of H L power minus 2 T inverse. Okay. Is equal to the dimension of K times theta divided by L. Okay. And therefore, you can see that the dimension of the thermal conductivity has to be H L inverse T inverse theta inverse. Okay. All the others are of course either length dimension or mechanical quantities, so they do not involve thermal energy. Okay. So now in this modified scheme that we have, there are now 5 dimensions. Okay. And therefore, there should be only 4 dimensionless groups. Okay. There should be only 4 dimensionless groups. One of them is the dependent dimensionless group, which basically involves the average heat flux. Okay. So, the dependent dimensionless group involves the average heat flux. It involves the dimension of thermal energy, and that dimension of thermal energy can be cancelled only against one of the other thermal energy dimensions in this problem. Those are either the specific heat or the thermal conductivity. Okay. You can see that the specific heat involves the mass dimension as well. So, if you use the specific heat, you will have to bring in one of the mechanical quantities. Using the thermal conductivity is simpler because it does not involve the mass dimension. Okay. So, my dependent dimensionless group, okay, has to involve the thermal flux, okay, times the specific heat, the thermal conductivity to some power A. Okay. And now you can see that there are length and time scales involved here. Okay. The length scale is of course equal to the diameter, okay, power B. Okay. There is a scale of temperature involved. Okay. So, I have to have theta power C. Okay. And then there has to be some time scale in the problem. We have to choose a quantity which has dimensions of time. Okay. We will just choose the velocity since it has dimensions of time, okay, u power d. Okay. So, that will be the dimensionless group that we assemble, and this dimensionless group has the dimensions h, l, t and theta. Okay. So, 4 dimensions, 4 unknowns a, b, c and d, and we can obtain each one of those explicitly. Okay. So, therefore, h power 0, l power 0, t power 0, theta power 0, okay, is equal to h l power minus 2 t inverse, okay, into the thermal conductivity power A, h l inverse t inverse theta inverse power A, okay, into L power B theta power C and L T inverse power D. Okay. So, with this I can get equations for A, B, C and D. The first one, if I take equal dimensions of H, okay, what I will get is that 0 is equal to 1 plus A. Okay. If I take equal dimensions of L, okay, I will get 0 is equal to minus 2, okay, minus A plus B plus D. Okay. If I take equal dimensions of theta, okay, I will get 0 is equal to A plus C. Okay. And finally, if I take equal dimensions of time, okay, you will get 0 is equal to minus 1 minus A, okay, plus D. I am sorry, minus D. Now, these can be easily solved. Okay. The first equation gives me that A is equal to minus 1 straight away. Okay. This equation here, since this is 1 plus A plus D equals 0, this gives me that D is equal to 0. Okay. This equation here will give me that C is equal to plus 1, I am sorry, minus 1. Okay. Yeah, there's a mistake here. The equation for theta, it should be minus A plus C is equal to 0. Okay, it should be minus A plus C is equal to 0, which means that A is equal to C, and so C is equal to minus 1. And from this equation, you should end up with D is equal to, I'm sorry, B equals. B equals plus 1. Okay. So, therefore, this dimensionless group that I have assembled this way will be equal to Q D by K delta T. Okay. That is the dependent dimensionless group. Okay. So, therefore, my first dimensionless group phi 1 is equal to Q D by K delta T. Okay. Let me give you a little bit of physical insight here. Okay, you could have got this without going through the details of the dimensional analysis, just by realizing that at the local scale, okay, at every volume element within the fluid, Fourier's law of heat conduction applies for the conduction of energy. Okay, and Fourier's law of heat conduction states that Q is equal to K delta T by L. Therefore, if I assemble a dimensionless group, okay, this applies at every local position where delta T is the difference in temperature locally. Okay. This does not apply for the unit as a whole. Okay. It does not apply for the unit as a whole, because convection is a very important part of heat transfer within this unit as a whole. Okay. So, this relation, Fourier's law of heat conduction, does not apply for the unit as a whole. However, if I scale the right and left sides of this equation, I do get a dimensionless group. Okay. Therefore, Q by K delta T by a length scale has to be dimensionless. Okay. So, for the dependent variables, I can use the constitutive relation to guess what is the form of the dimensionless group. Okay. So, that gives us the first one. As I said, there are 4 of them. The second one is relatively easy to guess. Okay. The second one is just equal to D by L. Both the diameter and the length of the pipe have the same dimensions of length. So, I can just divide one by the other and get a dimensionless group. Okay. There is a third one, okay, which involves the mechanical properties. That is something that we have seen in the last lecture. Okay. We showed that rho u d by mu was a dimensionless number. Okay. In this problem as well, you have rho, okay, you have u, rho, d and mu. Okay. So, therefore, I can very easily just write that the third one is rho u d by mu. Okay. That is a dimensionless group. Okay. Number 3. There should be 4 of them. Okay. So, the fourth one should contain the specific heat as well, because that is currently not involved in any of the dimensionless groups. Okay. The specific heat should also be a dimensionless group. Okay. And the specific heat has relations H m inverse theta inverse. So, it contains both mechanical properties and thermal properties. Therefore, I need to scale it by mechanical quantities as well as thermal quantities. I need to scale it by a quantity, an independent quantity which involves thermal energy, and an independent quantity which involves mass. Okay. The independent quantity that involves thermal energy is, of course, the thermal conductivity. Okay. As far as the independent quantity that involves mass is concerned, there are 2 of them, the density and the viscosity. Okay. You can, without loss of generality, choose either one of them. Okay. In this case, I will choose the viscosity, but you could very well have chosen the density as well. Okay. So, therefore, the dimensionless group that I will assemble is equal to Cp. It has to have thermal conductivity in it, okay, for the thermal energy dimension, the viscosity in it for the mass dimension, and then of course there is length, time and temperature, okay, for the length dimension, the time dimension and the temperature dimension. Okay. The length dimension of course will be d per c. Okay. The time dimension I can get from the velocity u per d, okay, and the temperature dimension I will get from the temperature difference. Okay. So, this involves thermal energy, the mass, length, time and temperature. Okay. So, therefore, my equation looks a little complicated. H power 0, m power 0, L power 0, T power 0, theta power 0 is equal to into the thermal conductivity, that is H L inverse T inverse theta inverse whole power A into M L inverse T inverse power B, okay, into the length power C, length inverse time power D and theta power E. Okay. So, there are a total of 5 equations that have to be solved. Okay. You would think it is a little bit complicated to solve 5 equations for these 5 unknowns. It turns out that if you solve these, okay, you get a pretty simple relation. Okay. The dimensionless group is equal to Cp mu by k. Okay. It turns out that the powers of the diameter, the velocity and the temperature difference are exactly 0. Okay. In this case, if you solve all 5 equations, you can do it yourself and verify. C is equal to 0, D is equal to 0 and E is equal to 0. Okay. So, you just get a dimensionless group which goes as Cp times mu by k. Okay. So, that is the final dimensionless group. Okay. I should write that as pi 4. Okay. So, therefore, the fourth dimensionless group that I have I will show you a little later how this dimensionless group can be inferred without going through this complicated dimensional analysis, by trying to give you some more information about what exactly these mean. Okay. But for now, we have got our 4 dimensionless groups. Okay. Now, of course, we have to assemble relationships between these dimensionless groups. Okay. From this point onwards, it has to be empirical. I will tell you in the next lecture what are the kinds of relationships that are empirically derived in this case, and after that I will go on to the other problem that we had, which was the mass transfer from a particle. Okay. So, we will continue with this thermal heat transfer problem in the next lecture, and then we will proceed to a mass transfer problem. We will see you next time.